the previous lecture, we were discussing the global convergence of a general descent algorithm to solve an unconstrained optimization problem. We have found that with the help of one of the inexact line search methods or with the help of the exact line search method, if we go for choosing the step length, then the algorithm is going to generate a sequence that converges to a point which is a stationary point of the given objective function. Now here question comes, is this stationary point always a minimizer, a minimum point of the objective function or not? So the question before us is that, can a descent method generate a sequence that is converging to a point which might not be of our interest? Precisely the question is it possible that the sequence xk generated by a descent method converges to a point x bar which is a saddle point or a local maximum point of the objective function? In this lecture, we shall try to identify an answer to this question, and we shall find out that yes, it is possible that a descent method is converging to a saddle point or a local maximum point of the objective function. We shall have two examples towards these two observations, converging to a saddle point and converging to a local maximum point. But we shall also get to know a fascinating result, that is the capture theorem, which tells that if a point, say x bar, is a strict local minimum of the objective function, then under certain mild assumptions on the descent direction being employed in the descent method and a mild assumption on the objective function, there exists an open set containing the point x bar, so that if you start your descent method inside this open set containing x bar, then the method will remain inside this set. That means the consecutive generated points by the descent method is inside this set, and ultimately the generated sequence xk by the descent method will converge to the point x bar. That is, this capture theorem crudely tells us that if a descent method comes closer to a strict local minimum of the objective function, then the descent method captures the local minimum point x bar. Let us now start finding answer to this question before us, that can a descent method converge to a saddle point or a local maximum point? Towards answering this question, at first I would like to mention a result that came out in the year of 2016, which tells us that let the objective function f, which is a function of several variables, be twice continuously differentiable and it has Lipschitz gradient, that is, the gradient of this function is a Lipschitz continuous function, and suppose that the objective function f satisfies the strict saddle property, where this strict saddle property means that any stationary point of f is either a local minimum or a strict saddle point. Then with the descent direction dk being chosen as negative of the gradient of f at xk, and with a random initialization and sufficiently small constant step size, that is, you take the sequence of step lengths alpha k to be such that all alpha k values are constant, say some alpha that lies in between 0 and the reciprocal of the Lipschitz constant capital L of the Lipschitz gradient of the function f. With this dk, alpha k and a random initial point, the descent algorithm almost surely converges to a local minimum point of the objective function f. This almost surely is a technical term. Interested readers can refer to the article that I will refer for the proof of this result. I shall borrow the result from an article entitled Gradient Descent Only Converges to Minimizers, written by J. D. Lee and co-workers. This fascinating result is found from this article, which came out through one of the conference proceedings of machine learning research in the year of 2016. This theorem, however, does not claim that a general descent algorithm cannot converge to a local maximum or a saddle point, since the strict saddle property does not apply universally. And therefore we are still in dark to find answer to the question before us, that whether a descent method can converge to a saddle point or a local maximum point. To investigate more detailed answer to this question, we at first crudely see that when we employ a descent method on a given general function of several variables that is just known to be having continuous first order partial derivatives, if we start the algorithm from any arbitrary initial point x naught, then we notice that the sequence generated by the algorithm, let's suppose xk, is such a sequence that gives us the sequence of function values fxk, a monotonically decreasing sequence. That is, we have corresponding to any given consecutive 2 points xk and xk plus 1, if xk plus 1 is strictly less than if xk. So if we start with x naught, then we are generating the next point x1, for which fx1 is less than fx naught, and then subsequently at x2 the function value is more reduced, and at x3 bit more reduced, and so on. So we are keep reducing the function values across the iterations. So even if this sequence of function values fxk is not converging to a local minimum value of the objective function f, we have substantially reduced the objective function value by moving through across these points xk's. Although there is a high chance that this reduced value of the function f at the end of the day is a local minimum, but there is no guarantee for any general function f that this sequence fxk is converging to a point which is a local minimum of the function f. But it is for sure that this sequence xk, if converges to a point say x bar, then this point x bar cannot be a strict local maximum of the objective function. This is due to this very fact that function values are getting strictly reduced across the iterative points xk's. Let us now prove this result that a general descent algorithm cannot converge to a strict local maximum of the objective function. The result neatly states that let the function f be continuously differentiable and the point x bar be a strict local maximum of the function f, then any descent algorithm, which we abbreviately write as general descent algorithm GDA. We shall use this abbreviation GDA throughout this lecture. By that we shall mean general descent algorithm. That is the algorithm that we have mentioned so far in the last two lectures, that you employ any descent direction dk and choose a step length alpha k by any of the exact line search or inexact line search methods. Then the ZDA cannot generate a sequence which once known as a convergent sequence cannot converge to the point x bar for any initial point x naught other than the point x bar. Let us try to prove this result To prove this result, let us assume that if possible, the sequence xk is generated by a descent algorithm, but this xk is converging to x bar. So on contrary, if possible, let xk be a sequence with x naught is not equal to x bar, that is generated by the general descent algorithm, and the sequence xk converges to the point x bar. Now here you notice that this x bar is a strict local maximum of the function f. Therefore, there exists a delta bar for which inside the open ball centering at x bar having radius delta bar, the function values fxs are all less than fx bar for any x inside this ball. So since x bar is a strict local maximum of the function, we have this inequality to be true inside this open ball. Now here we see that this sequence xk is assumed to be converging to the point x bar, and therefore with this delta bar greater than 0, there corresponds a natural number, say capital N, for which we have the norm of xk minus x bar less than delta bar for all k greater than equals to capital N. That is, after the index number capital N, the sequential terms xk's are lying inside this ball of radius delta bar. And hence, after this index number capital N, we have fxk strictly less than fx bar. Now, as the sequence xk is generated by a general descent algorithm, across the consecutive iterations, we have that fxk plus 1 less than fxk for every k starting from 0, 1, 2 and so on. Combining this line and this line, we have that for all k greater than equals to capital N, fxk is strictly less than fxk minus 1, which is strictly less than fxk minus 2 and so on. We shall end up with less than fx capital N, which further by this line is strictly less than fx bar. Now here we notice that this function f is a continuous function and the sequence xk is a convergent sequence converging to the point x bar, and therefore by sequential criterion of continuity we have the limit k tends to infinity if xk exists and it is equal to fx bar. But from this inequality we see that limit k tends to infinity if xk is less than or equal to this fxn, which is strictly less than fx bar, which is contradictory to the previous line that this limit k tends to infinity fxk is equal to fx bar. And hence our assumption that this xk converging to the point x bar cannot be a valid assumption, and hence the result follows that if a general descent algorithm generates a sequence xk which converges to a point x bar, then the point x bar cannot be a strict local maximum. So immediately you may now ask me the question that is it possible that a descent method can converge to a non-strict local maximum? Yes, it is possible. Towards this we shall have an example in the next that descent method can converge to a non-strict local maximum. Towards these, let us take the following function that is given by x plus 1 square if x is less than equal to minus 1. It is 0 in between minus 1 and 1. And for x greater than equal to 1, the expression is x minus 1 square. On this function, let us now consider employing a descent method with the initial point as x naught is equal to 3 by 2, the descent direction as negative of the derivative of the function f at the point xk, and we take the step length alpha k to be chosen by the Goldstein-Armijo rule, where we take in the Goldstein-Armijo rule the value of C1 is equal to say 1 by 8. We recall here that the Goldstein-Armijo rule with C1 is given by the Armijo condition that f at xk plus alpha k dk is less than equal to f xk plus c times alpha k into f dash at xk times dk, and the Goldstein rule f xk plus alpha k dk is greater than equals to f xk plus 1 minus c1 into alpha k times f dash at xk into dk. Now here for this initial point x naught is equal to 3 by 2. Let us now calculate the next iterative point x1. To calculate the point x1, we need to find what is the descent direction at x naught. The descent direction at x naught is given by d naught, which is equal to negative of the derivative of the function f at x naught. When x naught is equal to 3 by 2, we notice that the expression of the function f takes the expression of x minus 1 square, whose derivative is 2 times x minus 1, and hence the direction d naught is given by minus 2 times x naught minus 1, which is equal to minus 1. Now let us find the step length alpha naught, which is given by these two inequalities over here, the Goldstein-Armijo rule. To find an alpha naught by the Goldstein-Armijo rule, we consider here the inequalities of the Armijo rule at the point x naught. We keep alpha naught to be a generic variable alpha. This quantity less than equal to afx naught plus 1/8 alpha times this f dash at x naught times d naught, which gives us minus f dash x square, and hence we have the value minus 1 here. And the Goldstein rule is given by this inequality. That is, we need to find an alpha that satisfies from this first inequality, that half minus alpha square of it less than equal to 1/4 minus 1/8 into alpha, and this inequality which gives us half minus alpha square greater than equals to 1/4 minus 7 by 8 into alpha. From these two inequalities, you will find that the range of possible values of alpha is 1/8 till 7/8. So any alpha in between 1/8 to 7/8 satisfies the Goldstein-Armijo rule. Here now let us in particular choose the alpha node value is equal to say 3/4. We will get the next iterative point x1 is equal to x naught plus alpha naught d naught, which is equal to 3/2 plus this alpha naught is 3/4 times -1, which is equal to 3/4, and at 3/4 we check whether the gradient of the function f, that is here the derivative of the function f at the point x1, which from the expression of the function f gives us the value is given by 0, and the general descent algorithm will stop at the point x1, declaring that the point x1 is a stationary point. But here we notice that the point x1 is equal to 3/4 is a local maximum of this function fx. We look at the graph of the function f, which is 0 in between -1 to 1, and on the left side of -1 we have this parabolic part x plus 1 square, and on the right we have another parabolic part, and in this graph of the function we see that the point x1 is equal to 3/4 is a local maximum of the function f. Indeed, x1 is a local minimum, but it is also a local maximum, a non-strict local maximum. And therefore, what we get here that a descent method can converge to a non-strict local maximum, which we neatly write at the bottom that f dash x1 is equal to 0, and hence the general descent algorithm stops at the point x1, but the point x1 is a local maximum of the function f. Now next I will give one example where I will show that a descent method can converge to a saddle point. For which we consider a function given by f x1 x2, a function of two variables, as x1 square minus x2 square minus 2x1. For this function, the gradient and Hessian are given by grad f at any general point x1 x2 is equal to, the first component is the partial derivative of f with respect to x1, which is 2x1 minus 2, and the second component is the partial derivative with respect to x2, which is minus 2x2, and the Hessian matrix at a general point x1 x2 is given by, you please check that this matrix is the Hessian matrix of the function f. So here we see that if we equate this gradient vector to be the null vector, then we will get x1 is equal to 1 and x2 is equal to 0. So the point x bar is equal to the first component 1 and second component 0. Is the only stationary point of the function f. And at this stationary point we see that this Hessian matrix is indefinite, so the point x bar is a saddle point. Let me now show you that for a special choice of the initial point x naught and the descent direction dk, a general descent algorithm can be made to be convergent to this point x bar for this function f. Consider a general descent algorithm with the initial point x naught is equal to, say, the point 2 0, and take the descent direction dk by negative of the gradient of the function f at xk. And here in this example, let us consider the step length to be chosen with the help of the exact line search. With these rules for the initial point, descent direction and step length, let us now try to calculate the next iterative point x1. To calculate the next iterative point x1, we need to have the descent direction d naught available. See that at the point x naught, the descent direction d naught is equal to negative of the gradient at x naught, which is equal to minus 2 0. And to find an exact step length, we need to minimize the function phi alpha given by f x naught plus alpha d naught, whose expression you please cross check that is given by 2 minus 2 alpha square minus 2 times 2 minus 2 alpha. For a minimum point of the function phi alpha, we equate the derivative of the function phi with 0, and we see that this gives us 4 times 2 alpha minus 1 is equal to 0, which gives alpha is equal to half. Now at alpha is equal to half, we calculate the second derivative of the function, and you please cross check that this value is equal to 8, which is greater than 0, and therefore this alpha equals to half is a minimum point of the function phi. So we have the step length, the exact step length size is equal to the value half. With this step length, we calculate the next iterative point x1, which is given by x naught plus alpha naught d naught, which is equal to the point 1 0, and see that at this point x1, the gradient of the function f is the null vector 0 0, and therefore the algorithm stops at the point x1, which is the saddle point of the function f. So here we got an example in which we found that a general descent algorithm can converge to a saddle point. So accumulately, so far we have got one example where the general descent algorithm is converging to a saddle point. Here is an example where general descent algorithm converges to a non-strict local maximum, and here we have derived a result which confirms that a general descent algorithm cannot converge to a strict local maximum. In the next, we shall prove that once the sequence xk generated by a general descent algorithm gets close enough to an isolated local minimum, the sequence remains close and converges to the local minimum provided certain conditions on the step length and on the descent direction are satisfied. That is precisely the capture theorem, which states that suppose the function f is a continuously differentiable function and let x bar be an isolated local minimum of the function f, and there exist two positive constants, say alpha and beta, such that the step length alpha k is bounded by alpha and the descent direction to be employed, that is dk, has norm less than equal to beta times norm of the gradient of f at xk. We let these two inequalities are true for every natural number k. With this sequence of step length alpha k and descent direction dk that satisfies this inequality, let us suppose the sequence xk be the sequence of points generated by a general descent algorithm for any given initial point x0. Then the capture theorem tells us that we can find an open set, say omega, that contains the point x bar. The subsequent iterative points in the sequence xk also will lie inside the set omega. That is, once an element, say xp, lies in omega for some p in the set of all natural numbers, then all the subsequent points xk's also will lie in omega for all k greater than equals to p. Further, if we assume that the sequence xk is such a sequence that any of its subsequential limit is a stationary point of the function f, then we can prove that there exists a subsequence of the sequence xk that converges to the point x bar. We write it here that if any convergent subsequence of the sequence xk generated by the general descent algorithm converges to a stationary point, then we can find a subsequence of xk that converges to the point x bar, which is assumed to be an isolated local minimum of the function f. There is a subsequence of xk that converges to x bar. The proof of this result is a bit constructive, and therefore it is imperative that you please sit with a pen and paper and follow the steps that I would be writing. Notice that in the statement of this result, we have assumed the point x bar as an isolated local minimum point of the function f, and therefore there exists an open ball centering at the point x bar, so that inside that open ball the point x bar is the only minimum point of the function f, and therefore since x bar is an isolated local minimum of the function f, the point x bar is a strict local minimum of f, and therefore there exists certain delta greater than 0 such that x bar is the only stationary point of the function f inside the open ball bx bar delta, and we have fx bar less than fx for every x inside the ball bx bar delta. Now we construct an auxiliary function inside this ball bx bar delta in the following manner, that define a function, say psi, a function of one variable defined on the interval 0 to delta, given by psi t is equal to minimum most value of the function f inside the annular region t less than equal to norm of x minus x bar less than equal to delta minus the function value at x bar. That means in defining psi t, what we are doing, that we are considering the center at x bar, and the inner circle of this annular region is having radius t, and outer circle has radius this delta. Now inside this annular region, you take the minimum most value of the function f and subtract that minimum most value with the function value f at the point x bar. That gives the function value of psi at the point t. Now here, as this fx bar is the minimum most value of the function inside this entire ball bx bar delta, therefore for every given t greater than 0, we note that we have the psi t value greater than 0, and for any given pair of real numbers t1 t2 in between this 0 to delta with t1 smaller than t2, we see that the set of all points with t1 less than equal to norm of x minus x bar less than equal to delta is a superset of the set of all points x's that satisfy t2 less than equal to norm of x minus x bar less than equal to delta. And therefore, minimum most value of the function f in this set is smaller than the minimum most value of the function in this set. So we have here that psi t1 is less than or equal to psi t2, and therefore the function psi is a monotonically increasing function. Moreover, we notice that if we consider any point x dash inside this ball, then the psi value for norm of x dash minus x bar is less than equal to the function's value at x dash minus fx bar. This is due to the fact that you consider this amount of value is equal to, say, t dash. Then with this t dash, we go for calculating this psi t dash. Keep here this value t dash. Then notice that the point x dash satisfies this inequality. Then this minimum value is certainly smaller than the function's value at x dash, that is smaller than fx dash, and hence this inequality is followed. Now, given this construction of psi t and these three properties of the function psi, let us now try to see if the sequence of points xk's can somehow be taken into inside of this ball. Towards this, we go for calculating the distance between the sequential elements xk's with the point x bar. We see that the norm of xk plus 1 minus x bar is equal to xk plus 1 is given by xk plus alpha k dk and therefore this norm is less than equal to by triangle inequality that xk minus x bar its norm plus alpha k times norm of dk. Now, due to the hypothesis that alpha k is less than equal to alpha and norm of dk is less than equal to beta times norm of grad fxk, we have this quantity less than equal to norm of xk minus x bar plus alpha beta times norm of grad of f at xk. This inequality is true for every natural number k. Now in order to keep this xk plus 1 inside the ball of radius delta centering at x bar, what we have to make is this right hand side quantity less than delta. To make this right hand side quantity less than delta, we analyze that as limit x tends to x bar, norm of x minus x bar plus alpha beta times norm of grad of f is equal to 0 since the point x bar is a stationary point and this limit x tends to x bar norm of x minus x bar is equal to 0. And as this limit is equal to 0, there exists some positive number, say r, which can be taken smaller than delta, such that inside the ball of radius r centering at x bar, we have for any x inside the ball centering at x bar having radius r. Now with this value of r, we define an open set omega by the set of all points in Rn for which norm of x minus x bar is less than delta, and we have the function values at x's are less than fx bar plus psi r. We note that this set omega is an open set because this set omega is an intersection of the ball of radius delta and the set of all points in Rn for which fx is less than fx bar plus psi r. As the function f is a continuous function, this set being the preimage of the function f of the open set from minus infinity to mu, where mu is this quantity, is an open set. This set once is an open set, we certainly have its intersection with this ball, an open set, and hence this set omega is an open set. So we write here that by the continuity of the function f, the set omega is an open set, and also see that this omega is a subset of the ball bx bar delta. Now let us geometrically look the location of this set omega, that we had the open ball bx bar delta. Let's suppose this set is the open ball bx bar delta. Now you take the intersection of this open ball with this set, which is an open set in Rn. Let's suppose this is the open set that represents this set f inverse minus infinity to mu. We notice that this set contains the point x bar because fx bar is less than fx bar plus psi r, since psi r is a positive quantity, and therefore this intersecting region, which we define as the set omega, is an open set containing the point x bar. Now we suppose that the point xp, the pth element of the sequence xk, is inside this set omega. we let that xp is belonging to omega. Then certainly we have, by the definition of omega, that norm of xp minus x bar is less than delta, and we have if xp less than fx bar plus psi r. We shall prove that the point xp plus 1, that is the next iterative point after this xp, also lies in this set omega, and then by the principle of mathematical induction, any xk after the index number p will lie inside this set omega, and that will prove the first part of this result. Now, to prove that this xp plus 1 is also lying inside this set omega, we first have to prove that this norm of xp plus 1 minus x bar is less than delta. To prove this, that norm of xp plus 1 minus x bar is less than delta, we recall here that for any x dash, we have this third property, and in particular you take x dash equal to xp, you will have then that psi of norm xp minus x bar is less than or equal to fxp minus fx bar. So we write here that psi of norm xp minus x bar is less than equal to f of xp minus f of x bar, which by this inequality is less than psi of r. Now, as the function psi is a monotonically increasing function, from this inequality we certainly have that norm of xp minus x bar is less than r, because if this norm xp minus x bar is greater than equals to r, then you will have a reverse inequality here, since the function psi is a monotonically increasing function. Now this inequality, that norm of xp minus x bar less than r, and the inequality that we wrote over here, that for any x inside this bone of radius r, we have this inequality is true. Let us name it as double star. We get from this double star and star that norm of xp minus x bar plus alpha beta times norm of grad fxp is less than delta, and hence by the inequality that we have derived here, let us name it as triple star. Let us name it as triple star. We get that norm of xp plus 1 minus x bar is less than delta. So what we get here is that once you take the point xp is inside the open set omega, the point xp plus 1 satisfies this inequality, and by the decency of the direction dp, as dp is a descent direction of the function f at xp, we have f xp plus 1 minus fx bar is less than fxp minus fx bar, which in turn from this inequality is less than psi r, and hence xp plus 1 satisfies the second condition of this set omega, and therefore the point xp plus 1 as satisfies both these inequalities, this first as well as the second, we have the point xp plus 1 belonging to the open set omega. So what we see here that once xp is chosen inside the set omega, xp plus 1 is going to lie inside this set omega, and hence by the principle of mathematical induction we have xk belonging to omega for all k greater than equals to p. That is exactly what we wanted to prove in the part 1 of this result, the capture theorem, that there exists an open set omega containing the point x bar such that once xp is entering at omega, the next and subsequent elements of the sequence xk will all enter the open set omega. Now we shall prove the second part of this capture theorem, that if any convergent subsequence of xk converges to a stationary point of f, then the point x bar must be a subsequential limit of the sequence xk. To prove this, at first we look at the set omega, and we see that the set omega is a bounded set and contains all points xk's of the sequence xk after the index number p. By these two observations, we consider the closure of the set omega, and as the closure of a set is a closed set, so the set omega bar, the closure of omega, is a closed and bounded set, and hence by Heine-Borel theorem the set omega bar is a compact set as the sequence xk after the index number p is lying inside the set omega bar by Boolean-Weierstrass theorem. There exists at least one convergent subsequence of the sequence xk. Let us suppose one of these convergent subsequences of the sequence xk is, say, xkn. Let us suppose this subsequence xkn converges to the point, say, x star. Now, due to the hypothesis in the part 2 that any subsequential limit of the sequence xk is a stationary point of the function f, we get that this point x bar is a stationary point of the function f. We shall prove that this point x star is nothing but the point x bar, which is a strict local minimum of the function f. To prove this, we see that all these sequential elements xk's are belonging to omega bar after the index number p. And as this xkn is a subsequence of the sequence xk, then we will get an index number, say capital K, after which we shall realize that these xkn's are belonging to omega bar, that is norm of xkn minus x bar is less than delta, or let me take not delta but here from this star, that all the xk's after the index number p satisfies this norm of xk minus x bar less than r. So we take here less than r after the index number n greater than equals to capital K. You see that this capital K is identified in such a manner that we have this superscript Kn is bigger than equals to small p. As this Kn is a monotonically increasing function, because this sequence xkn is a subsequence, so once this xk is monotonically increasing and it is an infinite subset of the natural number set, we certainly have this Kn exceeding the index p after certain index number small n, and this index number is capital K. Now from this inequality we see that if we take limit on both the sides, then we will have on the left hand side x star minus x bar, its norm, is less than equal to r, and this r by the construction in part 1 is less than delta. And hence what we see that inside the open ball B x bar delta centering at the point x bar, we have the point x star, which is also a stationary point. But we notice that due to our construction of the ball B x bar delta, it is such an open ball centering at the point x bar that contains only one stationary point x bar. Now, as due to the hypothesis in the second part that x star being a subsequential limit is a stationary point, what we have here is that this point x star and x bar are identical, and hence the subsequence xkn is converging to the point x bar. And that completes the proof that there is a subsequence of xk that converges to the point x bar. Now we relook at the statement of the theorem, the capture theorem. Here in the theorem you can see that we have taken the assumptions that the step length alpha k is bounded by a constant alpha and the direction dk satisfies this condition. Under these two assumptions, we have this fascinating result that once the sequential elements xk's are entering in a close vicinity of the point x bar, that is this set omega, once xp is entering in omega, next and subsequent elements are going to enter inside this set omega, and ultimately this second part shows that xk's are going to capture the point x bar as a subsequential limit. So this is quite interesting that, well, we could not ensure that a sequence xk generated by a general descent algorithm converges to a local minimum of the objective function, but we at least have ensured here that under certain condition on alpha k and dk, that these two conditions, if we can somehow start our iterative points inside the set omega, then the sequence xk is going to generate a sequence that converges to an isolated local minimum of the function f. So this is also a broad achievement by the general descent algorithms, that we are not in complete dark. This theorem in fact informs that if we somehow can start the general descent algorithm from a close vicinity of an isolated local minimum, then the algorithm is going to converge to that particular point. But here you may ask me a question that the conditions that you have taken here, that for alpha k and dk, those are not mild assumptions. You may feel that this condition is okay, that step lengths are less than alpha, that is fine. It is quite a loose condition, but this condition on dk might be a very restrictive condition, but it is not really so. You see that usually in any of the general descent algorithms, we take the descent direction dk as simply the negative gradient of the function f at xk, or we consider dk to be some minus of a positive definite matrix times the gradient of the function f xk. Commonly we employ these two directions in any of the optimization algorithms, and we see that for these dk to be this negative gradient of fxk, this condition is trivially satisfied by beta is equal to 1. Now for this direction dk, if you take the assumption that this matrix capital dk, which is a positive definite matrix commonly taken as an approximation of the inverse of the Hessian matrix f at the point xk, if we assume that this sequence dk of positive definite matrices has bounded above eigenvalues, then we can quickly prove that this condition is satisfied. So the common choices of dk trivially satisfy this condition, and hence these two conditions, alpha k less than equal to alpha and this condition on dk, are quite relaxed conditions, and hence from the entire discussion in this lecture we arrive to the following answer to the question with which we have started our discussion, that can a general descent algorithm generate a sequence that converges to a local maximum or a saddle point? The answer to this question is that when the initial point is carefully chosen, the general descent algorithm majorly converges to a local minimum. By majorly, I mean that if these two conditions on alpha k and dk on this screen are satisfied, and if the point x bar is an isolated local minimum, then only the general descent algorithm converges to a local minimum. So there is a possibility when all these three conditions are not satisfied, that x bar is an isolated local minimum point, this condition and this condition are not satisfied, then there is no guarantee that the general descent algorithm is going to converge to a local minimum point. But we have proved a result here in this lecture, that a general descent algorithm cannot converge to a strict local maximum, and hence a general descent algorithm broadly converges to a local minimum or a saddle point. Now you may ask a question then, as the saddle points are not of our interest, that we are endeavoring to find a minimum value of the function f, can we have some light of mathematical conditions satisfying which we can escape the saddle points? You know, this topic, how to escape from the saddle points, is an hot topic of research currently. If anyone would like to have a few references for how to escape from saddle points by general descent algorithms, I would suggest you to visit the following four articles. Those are: the first article, in this reference entitled Escaping from Saddle Points, Online Stochastic Gradient for Tensor Decomposition, you will find that the authors have proved that for the objective function that satisfies strict saddle property, the general descent algorithm with the descent direction as the negative gradient, and by adding noise at each step, can escape all saddle points in a number of iterations, which is a polynomial function of the dimension of the argument variable of the objective function. Another similar article on escaping from saddle points is this reference entitled Gradient Descent Only Converges to Minimizers. Here you will find that under strict saddle property of the objective function, the authors have shown that a general descent algorithm with the descent direction as negative of the gradient of the function and with random initialization avoids saddle points even without adding noise. In this reference, authors have shown that by adding noise at each step, the descent algorithm can escape all saddle points. However, in this reference, although no noise is being added at each step, but no bound for the required number of steps or required number of iterations needed to reach at a local minimum is given. Another interesting article on escaping saddle points is this article entitled How to Escape Saddle Points Efficiently. Here in this article you will find that a general descent algorithm with the descent direction as the negative gradient can capture a second order stationary point, that is a point which is a stationary point together with
the Hessian matrix is positive semi-definite. This method captures a second order stationary point in a number of iterations, that is a polynomial function of the logarithm of the number of variables of the objective function. Here in the first reference, authors have proved that we can escape all saddle points in a number of iterations, that is a polynomial function of the number of variables. But here in this third reference, authors have proved that we can capture a second order stationary point within a number of iterations, that is a polynomial function of the logarithm of n, where n is the number of variables of the objective function. I would also like to add one more reference by Dixit and Vajda, a very recent article entitled Boundary Conditions for Linear Exit Time Gradient Trajectories Around Saddle Points. Here you will find that the authors, Dixit and Bajwa, proposed a descent algorithm regularized by some boundary condition related to Hessian matrix, which can exit the vicinity of the saddle points in linear time. Therefore, in accumulating all the results that we have described and came to know in this lecture, we obtain the following conclusion, that once a descent algorithm is employed on finding a local minimum of a function that is known to be continuously differentiable, we end up with getting a stationary point, and this stationary point in general can be anything. It can be a local minimum, it can be a local maximum, it can also be a saddle point. However, under certain mild conditions on the step length and the descent direction, we majorly get converged to a local minimum, and a general descent method can never attain a strict local maximum. And there are nowadays quite a bit of research how to escape the saddle points which are being generated by a general descent algorithm. So we conclude that a general descent method converges almost always to a local minimum point of a continuously differentiable function. With this comment, I end up this lecture here. Thank you all for all of your kind attention.